Okay. The last part is the frequency domain analysis by using the PST or power spectral density. In frequency analysis, we have different type of analysis. The most important and maybe the most famous methods are FFT and PST. But generally, we prefer to use the PST because of some advantages. For example, the first one, the results in the PST are independent of sample length. I mean, for example, if you have a signal for 5 seconds and find the PST, and again, if you do the PST and extract the result for a signal with, for example, 15 seconds, the results must be the same, and the length of the signal does not have any effect on your results. The frequency resolution or bandwidth can be explicitly defined in the PST, and you will see later in the results I will explain how. Easily we can integrate the results to find the velocity and the displacement without any filter, without any other modification. We can find the results for the displacement and the velocity. And finally, we can easily calculate the RMS values for the straight from the PST. Here you can compare the FFT diagram for the different signals with different lengths, and also the right diagram is the acceleration versus frequency, or the PST, again for the same signals with different lengths. Here you can see the blue line is the signal with the length 1.1. The red one is for the signal with the length 5.5. You can see that the amplitudes are changed, and even the position of the amplitude of the peak points are changed when you decrease or increase the length of the signal. But here in PST, by changing the length of your signal, the results are the same, and all of them have the same peak with the same position. So this is one of the most important advantage in a system, a PST analysis. When you use in a system, you can see by changing the length of your signal, you can get the same results. So here you can see again effect of the lens for the bearings. The blue one in the left diagram, the length is 0.125 seconds, less than 1 second, but the red one is 10 seconds. And you can see the FFT results are very different, but PST is almost the same for both lenses. As you can see, the lens does not have any significant effect on the results. To calculate the PST, usually you can use your own code. I mean, you can write your own code by using different softwares, and the procedure is clear. You can refer to the different reference, but here this is a very short review to the procedure to extract the PST from a signal. But generally, you should know that PST, in fact, is based on the FFT, which is the fast Fourier transform. But in PST, we divided the signal into different segments, and we calculate the FFT for each of these segments, and then we compute a FFT on each of them and find the overlapping for each segment, and then by using the square the results of the FFT, we can find the PST for that specific signal. So in fact, the PST is a normalized form of the different segments of a FFT. Here you can see the PST of the bearing signals. The purple one is the normal bearing, and the green one is the signal with fault 007. Again, the important part in the signal in frequency domain is the peak points. As you can see, for the normal one, we have one peak here, which is about before 20. We have another peak here, we have one peak here, we have one peak here. And if you compare with the fault signal, you can see that the maximum peak for the fault signal is here around 1000, the green one. But for the purple one, the peak is here before 100, and it's about 90 hertz. So you can see the frequency of the normal one is significantly less than the bearing with fault. And in the time domain analysis, when we extracted the displacement and velocity, you saw that the amplitude of the velocity and displacement for the normal bearing were more than the fault bearing. And this is the reason. Here you can see we have a lot of frequency in low frequency in comparison with the fault bearing. And if you separately look at the signals for the normal one, you can see that the frequency is 90 hertz, the maximum peak. And its value is about 473 micro times by G squared divided by hertz. And for the fault signal, you can see that the maximum happened at frequency 1051 hertz. So you can see there is a significant gap between the normal signal and the fault signal. And if we extract the results for other faults, you can see by increasing the fault, this peak frequency has been increased. So it can be one of the criteria that you can consider in monitoring of your system. But as I told you, usually we use the time domain analysis for the condition-based monitoring, and we use the frequency analysis to extract the characteristic of the system. Here you can see that, for example, for the system with normal bearing, the frequency is 90 hertz. So easily you can calculate the frequency of your system. And here you can see for all of the signals, we have one peak around 30 hertz, as I shown here. We have one peak for all of the signals with different faults. And this peak is due to the frequency of the motor. If you remember, in the first slide, I mentioned that the frequency of the motor is 1772 RPM or 185 radian per second or 29.5 hertz. And here you can see around 30 hertz. This is around 3. So about 30 hertz. We have one peak for all of the signals, and this is due to the frequency of the excitation. So it's very important, for example, in the system with normal bearing, if this speed shift to about 90 hertz instead of 30 hertz, we will have the resonance. And in your motor, you will hear a lot of noises which show that your system is about to the resonance phenomenon. To calculate the RMS, easily you can calculate the acceleration RMS by using this equation, the square root of integral PSDF that df. So we need to calculate the area for the acceleration in the PSD diagram. So if you calculate this, the RMS, again for different faults and for the normal bearing, you will see an increment in the faults. And if you compare with the time, you will see the results are the same. The RMS from PSD and the RMS from time, the results are are almost the same for normal and for the fault bearing. And this error is very low and it's acceptable. So with a good accuracy, you can calculate the RMS for the signal in the frequency domain. And to calculate the velocity and displacement, easily you know that in the frequency domain, for the velocity and acceleration, only we need the frequency of the system, omega. So by dividing by omega squared, acceleration by omega squared, you can calculate the velocity. And by dividing the acceleration by omega to the power of 4, you can calculate the displacement. So you don't need any modification. You don't need to use any filter or any taper to calculate the displacement and velocity. And you can directly, without any integration, you can calculate the displacement and velocity. So usually, if you want to find the velocity and displacement signals, you can use the frequency domain analysis because it's easier and you can directly find the displacement and velocity. And here you can see the RMS for the different frequency ranges. As you can see, this part is for the frequency between 1 to 65 hertz. The RMS for the frequency between 65 to 300. I mean, in the integral, when you calculate the PSD, PSD is a function of the frequency. So we calculate the integral on the frequency. The interval of this integral can be changed. For the first one is from 1 to 65. For the second one here is from 65 to 300. And finally, for the last one is from 300 to 6,000. You can see for the first two ranges, 1 to 65 and 65 to 300, the RMS for the normal one is more than the fault one. But in the higher frequency ranges, from 300 to 6,000, you can see that significantly the RMS of the fault bearing is more than the normal one. So it can be another criteria to find out the fault effect, especially in a high frequency. If you calculate in the high frequency, calculate the RMS, if there is a significant error, you can see there is a very huge gap between the fault one and the normal one. So in the high frequency, you can easily observe the difference between the different fault and the normal one. So I already explained this. Okay, to calculate these results, as I told you, the first step you need to extract the data. For this purpose, you can use different type of sensors or different type of equipments. But the equipment that I use and I suggest you to use is the accelerometers, the portable accelerometers and the wireless sensors that you can use them. You can easily attach them to your structure and then you can collect the data, and then you can move them to your system, to your laptop, to your PC, and then you can, by using different software, you will be capable to do the analysis in time domain or in frequency domain. And the last step is do the analysis. So for this purpose, we need different sensors. We have different types with different brands, as you can see here, some of them. These are some of the most important sensors that all of them are wireless. You can easily and they are portable. I mean, you can attach to your structure, collect the data, and then you can use the data to your analysis. This is the NQ sensor that we already have it in USB, and we use it in our projects. Already we are working on energy harvester and using a vibrating system in an energy harvester. By using this sensor, we are collecting the data and do the analysis to extract the characteristic of our harvester. So conclusion, so we will have first a vibration data. This data can be collected by using the different sensors, and then we can do the analysis on this data by using the different softwares, different codes, and then we can do the monitoring of your results. According to the results, according to the data, we can monitor the behavior and the condition of our system. Okay, thank you for your attention. And by this slide, we can wrap up this course for this semester. Okay, thank you for your attention. And after 10 minutes break, we can start the tutorial.